Recurrent neural networks are great at handling sequential data. But they have a critical flaw, the vanishing gradient problem. When sequences get long, gradients shrink to nearly zero during backpropagation. The network simply forgets what happened many steps ago. Long short-term memory networks, or LSTMs, were designed to fix exactly this problem. They introduce a special memory cell that can store information across hundreds of time steps, giving the network a true long-term memory. An LSTM cell has two flows of information, the hidden state, which works like a short-term working memory, and the cell state, which acts as a long-term conveyor belt. Information can be added to or removed from the cell state through three carefully designed mechanisms called gates. These gates use sigmoid functions to output values between 0 and 1, controlling how much information flows through. A value of 0 means block everything. A value of 1 means let everything through. The first gate is the forget gate. It decides which information from the previous cell state should be thrown away. It looks at the previous hidden state and the current input, and outputs a number between 0 and 1 for each value in the cell state. Values close to 0 get erased. Values close to 1 get kept. The equation is Ft equals sigma of Wf times the concatenation of Ht-1 and Xt, plus the bias Bf. The sigmoid function ensures the output acts like a soft switch, selectively filtering memory. The input gate handles what new information to write into the cell state. It has two parts. First, the sigmoid layer decides which values to update, this is the input gate IT. Second, the TAN layer creates a vector of new candidate values, C hat-T, ranging from -1 to +1. These two are multiplied together to form the update. The cell state is then updated by combining the old cell state scaled by the forget gate, plus the new candidate value scaled by the input gate. This is the core memory update equation. The output gate controls what parts of the cell state to expose as the hidden state. A sigmoid layer decides which parts of the cell state are relevant. The cell state is then squashed through a TAN function to push values between -1 and 1. Finally, these are multiplied together to produce the hidden state HT. This hidden state is what gets passed to the next time step and also serves as the output of the current cell. The key insight is that the LSTM can maintain relevant long-term information in the cell state while only exposing what's needed right now through the hidden state. LSTMs power some of the most important AI applications. Language translation relies on LSTMs to remember context across long sentences. Speech recognition converts audio streams to text using sequential memory. Time series forecasting for stock prices, weather patterns, and energy usage all benefit from long-term memory. Anomaly detection in fraud and cybersecurity use LSTMs to spot unusual patterns. And recommendation systems use them to understand user behavior over time. The LSTM remains one of the most battle-tested architectures in deep learning.